what I can say.
Hey, welcome to Coffee Compiler Club. Here to talk about compilers and language runtimes and typing systems and compiler IRs. And Alan, you said before on Discord that you wanted to talk about a different version of an IR, possibly based on recursion instead of looping. And
Yeah.
Cameron, you are now floating sideways gradually in space across your seascape, sandscape, just to let you know.
Um, okay. So so we discussed the recursion versus the iteration, and I mean, I got the sense that you liked iteration. Okay. And the reason you liked iteration was that it made things simple to think about and it was easy to optimize. And that was sort of confirmed by these papers I found, which said that iteration was of less computational complexity than recursion. So specifically, right, so it's very different because you have unrestricted recursion and
Okay,
unrestricted
for
iteration
the
are
for the
equivalent.
audience who's yet to come, the difference here between like computability and expressibility and sort of ease of optimization as opposed to any particular optimization. Like this kind of things you get out of iterative based optimizations or the shit that happens in like Fortran C compilers. These things are good for 2x to 10x over other approaches, sort of fairly easily, obviously, for the last 50 years. And this shows up all the time. And the ultimate in for people who start with a highly functional language, say Haskell, and they drop it down as they miss a lot of performance, and they end up in in an iterative space to get any kind of performance out. So they do drop it into an iterative space, and then the hardware is all iterative. Anyhow, the hardware is not functional. It's like, no, it's all stateful and iterative. So you got to go to what the hardware does. Okay, with that aside, go.
Yeah, so okay. Well, there's also tail calls. So tail calls are weird because they're not really recursion or iteration. They're like lower level than both. Because like it turns out like when you have like a jump instruction in assembly, right? It just jumps. It doesn't like it's very
Yep.
simple. It doesn't change anything, and you don't need recursion, you don't need iteration, you just jump.
Right. And
Um,
just to be clear, when I said iteration, I was thinking of moving it down to the hardware level, which includes just jumps. So hardware guy, and then the IR that I use to implement on the hardware is all full of jumps, basically.
right.
That's
And so
part and parcel.
so
Yes,
when you
tail
have
call recursion optimization seems like a lot of syllables to use to say jump.
A jump. Yeah.
yes, yes. So I mean it's yeah, I should stop saying tail calls. I should say jumps.
But we get the idea. So what are you trying to do here?
Okay. Um, so where was I? Okay, right. So recursion is well, so you mentioned two things. So there's expressiveness and there's computability.
Yeah.
Um,
Okay. Yeah, I
so
mentioned, but I'm not really interested in computability. It's expressiveness, and then boil it down to can I
so
optimize?
so for me both of those are interesting. And so in particular expressiveness is interesting when you're writing the source language. So if you have like the high level,
Yeah.
source programming language, and you're like, well, if I should I implement recursion or should I implement iteration? And the answer with regards to expressiveness is you should always implement both because why would you leave one out? That's just stupid. Um, but the real answer is that if you had to pick one, you were stranded on a desert island, right before the mid-level IR, and you had to pick one, you would pick recursion because recursion is it's the easiest way to express well recursion obviously. So I mean you express recursion in terms of itself, that's a normal way of expressing recursion. Um, and then the other thing is iteration. It turns out you can implement these kinds of macros. And so there's like a paper I found a scheme paper on how to implement loops as recursive macros. And so you say like a while loop
I don't think
is like,
there's no one here disbelieves you can implement one and the other, or one can be used to implement the other. It's more a question of I'm not stranded on a desert island. I get to pick them both. And there is an ease of manipulation that comes with iteration. That's a different ease of manipulation that comes with recursion. They both have their strong points, but things I can do with iteration easily, not the arbitrary effort, but with easily, are different from the things you can do with recursion. And the things that go with iteration tend to directly map onto hardware, followed by very large integer factor speedups. So I don't say that
Yeah.
they should have one or the other. We're going to take both. Okay. But my
Well,
focus on an IR is to drive the last mile down to the hardware. That's my focus on an IR, drive the last mile down to the hardware.
so I was getting there. Okay. So
Okay.
you have the so in the source language, okay, so you want to keep the core of the source language as small as possible. And
That's
that's
a,
because the smaller the language core is, the easier it is to learn. Okay.
I, I will point out that many successful languages have gotten fucking huge. Not to
Yeah.
mention C++ or Java, but yeah, okay. That's a design philosophy on the source language. It has nothing to do with the IR.
Yeah.
Yeah, I
So there's
tend to
there's
agree with
actually
that
actual
statement,
disagree.
but for a different reason, that if you keep the source language small and you implement most of the language features in the standard library,
Yeah.
you can get people who like your language to work on your language because they don't have to work in a language that's not your language.
Ah,
right.
ah.
Like it
Yeah,
is kind of nice that the Java standard library is written in Java and you don't have to write C++ code to make a lot of changes to the Java standard library.
yeah. All right, sorry.
Okay.
Go, Alan, again.
Yeah. So you have this, okay, and so basically, I mean, I decided this a long time ago. I was like, iteration is going to be the macro stuff, and then the core of the language is going to be recursion. Okay. And so that was when I was writing Strausscut several years ago. And so now like I'm coming back with like a fresh mind and like, I'm like, okay, well the language is designed. Now how do I compile it? And that's where the intermediate representations come in. Um, and that's sort of the issue is that it's actually very hard to optimize recursion. Um, and so the answer is after you've gotten rid of all the iteration, you actually want to start adding it back. You want to say, I have this recursive program. Where are the loops? And, find every loop you can and turn it into a loop. And then you optimize the loops. Um, and
I mean,
yeah.
this is what
So how,
Haskell and OCaml and folks like that end up doing.
yeah.
I don't
And
know how
so
much you can
it's,
do it by analogy, though. I've heard lots of people talk about loop optimizations of peeling off the first iteration, doing a bunch of checks there, and then not doing
Yeah.
those on the other iterations. I haven't heard people talk a lot about, oh, I know that this function is recursive, so I'm going to make one copy of the function that is to be called by the rest of the world and one copy of the function that is only the implementation if it's called from the function, because I have stronger assumptions if I know that it's only the internal call sites and the checks have already been done. Like you could do a lot of that same peeling analogy with a function
It rapidly
that you
turns
could do with a loop.
into you need an IR that lets you express loop structure so that you can do like loop invariant code motion and the like. And that means suddenly you're staring at an IR that's lower level and supports control flow directly and can then be optimized at that level. And you still have recursion and you want it, but you need to have an IR that lets you manipulate loops. You get
Right,
arbitrary
so my question is,
graphs.
why is loop invariant code motion different than recursive call
Uh,
invariant code
so
motion?
for what it's worth, Haskell compiler GHC does have optimizations for recursive function, and it can turn them into various consumer patterns that are able to hide some of the recursion internally and rewrite one version of recursive function into more efficient function. So you do have optimizations on recursive functions.
No, I know you can turn them. I know Haskell exactly. Yeah, turns it into something you can do a loop with. And then now it's got a loop. It can do whatever loop optimizations are done, typically with a class. I would guess, I don't know, with a classic loop optimization strategy, which involves finding loops and finding back edges and doing code motion based on that and the like. So what you
Peel the
said, Aaron,
first, peel the last, unroll the middle.
what I heard you say was get yourself where you do loop things, and now you do loop things. But the get to is sort of kind of understood, but the actual effort on the loop things is significant. And so you need to have an IR that supports, I want to say, control flow and looping fairly directly so that you can reason about how your loop things do. It is non-trivial to do these optimizations, optimizations, even with an IR that supports it. That's why you want the IR to support it because it's non-trivial. It's difficult. And so what I'm hearing, maybe hearing, maybe not hearing, is Alan coming around and saying, having gotten rid of loops and gone to recursion, that's great. And Haskell and OCaml all went there, but a bunch of people do. Okay. Now I unwind and come back. Yes. You end up with, I think you'll end up with two IRs, one which is basically recursion based, but one which kind of sets itself up to be a loop, having discovered the limits of recursion, the bounds of recursion. Now I've declared a loop. Then I want to do loop things with it. And that's a lot of work too.
Yeah, so this is actually reminding me this paper Secrets of the GHC Inliner. Um so like what they say basically is that they don't deal well with recursive functions. Um so like the way they handled it is they find a cycle of the functions. And then what they do is they just sort of arbitrarily pick what they call a loop breaker. And they're like, okay, we have,
Yeah.
this cycle of functions, and we're going to say this one is the entry point.
Yeah.
And then the rest are like sort of inlined into that as like,
Right.
and so, and that's also the definition of a loop is you pick an entry point and then you have
Yeah.
jumps in
So,
between the
so,
loop.
so let me add here some color. In the non-Haskell functional world, C and Java, Fortran, the like, it is most commonly the case that your loop header is well defined by the program and the structure, and a simple loop finding algorithm will find the header when it finds the loop at all. As soon as you go to a place where I have multiple inline functions that are calling each other and go to recursion, I can enter them at any point. Then I have a classic irreducible loop. Irreducible loops do not optimize easily under any loop strategy. They have all kinds of issues with that, and they're usually turned into reducible loops via various kinds of cloning, which would be inlining, until you've picked an arbitrary header. And in fact, C2 sees that directly every day in the Java code. People accidentally write irreducible loops. You can't do it easily in Java, except that you can without meaning to. And so, which one's the loop header? Eh, you pick one. And maybe I'll have two or three entries, but the scenarios you're talking about, Alan, you might have 10 or 15 entry points into the loop. And now, which one is the header? Why? Yeah. I get frequency info for hotspot and don't have so many choices, so I can pick one, not too much difficulty. Having picked one, then there's a bunch of work to goes to make that loop now reducible and get rid of the bonus extra entry points.
Yeah, and I think that's really the thing is that it's easier to determine if a loop is reducible than it is to determine if this set of recursive functions is corresponds to a reducible loop because you
Has to
have
be
like
one, has to be one that dominates all the others. You
yeah
call the first one first, and he calls the others in whatever pattern he does. And then everyone eventually calls him again, I guess. That's the loop.
yeah like because when you have the recursive functions you don't have an entry point, and when you have a loop you have a designated entry point, and so that's essentially what turns recursive functions into loops is you designate the entry point, I think.
Yeah. The other thing going on with your scenario I've seen is a bunch of folks call each other internally. And so that you get a strongly connected component of all the function calls that all call each other. And in the land of sort of higher performance computing and loop optimizations, you want to turn that into a loop nest and declare an inner and an outer, but they all touch to each other. It's all same strongly connected component. Go discover the actual nesting. And again, I get help out of profiling data from the hotspot runtime. Otherwise, it's kind of arbitrary if you don't have any hints. You're going to get the wrong things, the inner loop and the outer loops, or you'll just make them a giant mess and not declare a loop structure, not be able to declare a reasonable loop structure. I don't know.
How does Java users accidentally end up with irreducible loops? That sounded kind of funny.
Yeah, so it first started showing up when people did nested try-finalies, typically around I/O things where they're trying to do network recovery things. And every finally was essentially a jump from somebody who can throw to somebody who can catch. And then you would do on-stack replacement. And that was, you compile the main function that was all the performance was going to. And then the next entry point, you use the compiled code. And there was no next entry point. You were just in this infinite loop forever, like any server says, while true, serve things. So you make an on-stack replace, which means you start in the middle of the loop and say, this is my entry point. And then I'll go from there. Well, that in combination with nested try-finally catch blocks turned out to have irreducible loops, strong high-performance loops that burned a lot of time and could well benefit from loop ops, but they started life irreducible.
Finally, try finally is always a bad friend.
Yeah. Yeah. It basically says it's some straight line code. I have 27 jumps to here. Well, if here's where I looped back to here, whatever, I intercepted somewhere in here, then these 27, one of them will be irreducible, but probably a bunch of them are irreducible. Yeah.
But if you're lucky, that try-finally is rare enough that your optimization just says, if this happens, deopt.
It wouldn't. So the other thing was the exceptions were being caught by C2 because they were high performance and rethrown because the user knew he didn't want to have a new fresh exception, or I could trace that it was dead and throw it away. So the one of the standard IO things throws for a stupid, I don't want to say it's file not found or something. Somebody throws that it should have had an error code, right? And so C2 says, yeah, I'll catch, file not found. Yeah, fine. Oh, look, it's dead. The next statement, just a Boolean test after they caught the thing and flagged it, whatever, fine. I don't know. But a bunch of these things would show up specifically around deeply nested enterprise IO handlers. And that was just exactly where they wanted the performance. So that's where we focused on. And that's what we got. And oh, look, this bad performance is because we're starting with an OSR. And the OSR immediately says, I jumped into the middle of the hot inner loop. And that's a second entry point because the fall around package of what would be the classic loop has to compete with the fallen path from the OSR. So then I got 2 entry points into the innermost loop. So I have to peel and peel and peel and peel. And you OSR your way from the triply nested loop. So the OSR says finish the innermost loop iteration as a standalone peel. Then I have an outer iteration running the inner iterations with a standalone outer peel, and then the triply outer peeled and the doubly nested loop. And then I finally fall into the top of the actually full triply nested loop where I can, do all kinds of loop invariant hoisting games out of the inner loop, and having already inlined all the try catch finally things that all turn into go-tos, and then, oh, look, it's fast. Never mind. Fine. Ugly.
I was going to say it's more common now with the using construct, which is basically a shorthand notation for try finally.
Well, I guess I haven't seen that one. I left if that one came around, so I don't know how they implement it.
No, it's not in Java yet. I think it's in C# though.
Okay.
JavaScript also is getting it or got it.
I thought using was just splat a namespace into this one.
So using is a try finally under the covers.
Really?
Yeah, I think is it
Java
like a
calls
with
it-
statement? Like
Java
in Python?
Java calls it try with resources.
Oh, Java try with resources to try finally. Yeah. Okay. But I've never heard it called using. I see.
So there's no reason
Java,
to have the complicated Java syntax. So C# is like, let's just call it using.
Yes, it makes try finally like hardly worth it for the amount of try with resources, because the amount of bulk syntax. It's just huge. I've tons and tons of times in C++, I would get, basically try finally or try with resources by declaring a stack object variable that had a destructor.
Right.
When you went out of
Yeah.
scope, ran the destructor. Okay, fine. That's
They
your,
call it RAII.
yes. Hotspot is full of that. It was very, very helpful. But then, fine. And I don't understand why it took Java 20 years to figure out that try try finally was not try with resources or whatever. Finalizers were not try with resources. Never mind.
Well, I have destructors and Strauss-Cut, so
Excellent.
they're just undecidable. So but they work, right? If you can implement them, which is
That's your problem.
honestly, yeah. Like I mean, I've read the static verification papers, and I probably need to find like a whole nother like research group with like we work in static verification just to get that accomplished. But anyways, so back to this.
This is a classic language designer's problem.
Yeah,
Design a language you can't implement. No one can implement.
yeah.
Well, and
Uh,
the edges of life cycle have all the scary parts, right? Like
Yes.
construction in Java is a fucking nightmare.
Yes. Yes.
Initialization and construction.
okay, so the other thing. Okay. So I mean the iteration, the versus the recursion, the answer is just you want both. You want both of them in the source language and you want both of them in the intermediate language, but you don't want it in between, you just want recursion. So
I don't
you
know
get
about
this
that one.
so you get this kind of like 1-2 sandwich where it's like, like an hourglass figure sort of thing.
Maybe. I
Yeah,
Um
I'm not
claim
really
that.
following. What do you think you gain by forgetting about the loops and then relearning them? Because
Yeah.
I feel like Java forgot about a bunch of types that the JVM then had to relearn, and I don't know that that was helpful.
Turns out he has to do the loops too.
well
And
the sorry. I
no, that's
mean,
okay. In the very high, very long term, very high end, everybody gets better performance. It is beneficial to be able to relearn all the loops because you'll discover things that weren't loops that are actually loops and the like out of his recursion cases, what's actually the hot loop will eventually show up and you'll get to optimize it, even though it wasn't declared that way at the source language. I can certainly write you tiny programs that say things that say,
So you think
have a
there is a
doubly nested
superset
loop.
of loops you can detect by forgetting them and relearning them?
Yeah, you relearn them anyhow. You relearn them anyhow. Suppose I tell you, here's a nested set of loops. It says 4 equals 1 to n, 4 equals 1 to m, do something in the hot inner loop. But then I set the trip count of the inner loop to 1 and the trip count of the outer loop to 1 billion. And the outer loop's the hot loop and the inner one is not hot. And I'd rather have the inner loop say, if m is 1, do one thing, and now this is my hot right else. Okay, now I have to do something funny if you screwed them. But you can reverse the hotness of what loops are. So C2 would typically just look at the profiling data and say, I'm going to ignore the nested inner to outerness that you fed me in the first place and restructure to get the hot on the inside. And then I'll take all the repetition out of the hot loop. And but the same kind of things happens when you had all kinds of other control flow, like these tri-finalies. There was some big loop somewhere, but then they jumped left and right and they threw and they caught and they threw and they caught and suddenly they had hot loops in weird places because of that.
Does that sound like what you're doing, Alan?
um I mean, I'm not writing a compiler yet, so and the answer is no. But it sounds like what I want to do. So, but let's see. So the other thing is like is control. So I was looking at simple, and so simple has control edges, right? So there's like the if statement, for example. You have like a control edge, and then you have the if statement, and then it has two control edges out for the different cases.
Mhm.
And so Haskell, you don't have that. You have lazy evaluation, and
Hmm.
so there's this like completely separate system that decides what is evaluated when.
Right, right.
You have like the data flow, and conceptually, so there's different ways to think about lazy evaluation, but I think the right way to think about it is that you have a choice of evaluation strategies and you pick the right evaluation strategy that will get you the answer the fastest. Um, and
That's a very Oracle-based evaluation strategy. Fine.
Yeah, and so like you have all these hacks for figuring out like what is the fastest evaluation strategy, and you probably have to use profiling data just to figure that out, right? And so like
Have it. Yeah.
sometimes it's faster to do eager evaluation and just go straight line through the code. And other times it's faster to like make a thunk and delay the evaluation. And then maybe you evaluate it, 100 lines later or something when it, actually you've like gone through several cases and you're like, oh,
Or
well,
you,
now I actually need this.
right, or you didn't evaluate it, which was the savings.
Right. And then you save a lot by if you
Save
don't
a lot by
evaluate.
not doing it. Fine.
Yeah. And so that was the thing I was looking at before this was like trying to figure out how to get rid of control edges in simple. Um, I was not having a good time
There you
figuring
go.
that out.
So
So
like the control edges are part of what goes down to the hardware in the end. So there may be a time if I started from a lazy language, I might have a format or IR that let me think about the laziness and whether it's better to evaluate now or to stall. But when I'm boiling down to the hardware, all I'm going to get is jumps, branches, go-tos, or not. So I want the control flow directly represented in the IR, so I directly know whether I'm getting jumps or not when I put them out, and then whether or not it's time to do something about the jumps. Too many jumps, I can do something.
right, right. The question is when do you fix the evaluation strategy? When do you say like I have this, mathematical equation like 1 + 2 + 3 or whatever, and you're like, well, okay, I've decided I'm going to evaluate the 2 + 3 first and then the one or whatever.
Right, right.
Um,
I
yeah.
mean, this sounds like something specifically to Haskell with lazy evaluation as the default. There has to be some experience papers in the Haskell community about how they tried different things and what was better and what was worse. In
Well,
your
no,
particular,
because so that's the thing is Haskell like it doesn't it still has a fixed evaluation strategy. That's why people say like Haskell laziness didn't work out for them. And it's because they have this very like strictly defined strategy, which is it always defers things as much as possible. And it turns out that's bad because they defer it too late in a lot of cases. And so then you're right that they came up with like a bunch of like heuristics for like when to eagerly evaluate things, but they didn't do that in like the core. They did it in the source language. And so you try to use Haskell and you end up with like basically needing to think about whether every diff expression is
right.
evaluated strictly or lazily. And I guess it's getting better. They added syntax for it and stuff, but it's still to me it's the wrong approach. You want to just write a really complicated expression, and then you want the compiler to use the profiling information to say this is how we want to evaluate it. We want to evaluate this first and then
Well, it says
this.
that your semantics look a particular way, like they look eager, and then it's up to the compiler to decide that I'm going to delay this or not. But he just does the
Well,
as if rule, and you can't tell the difference semantically. It just runs faster.
yeah.
The moral equivalent of that in
Well,
the iterative imperative world is simply dead code elimination. You
okay,
just
so
compute
there's
something, and compiler says, "Nah, you're never going to use it, so I'm going to throw it away."
Yeah, so there's the issue that like you can't actually have a purely eager semantics for it because sometimes you get expressions that take an infinite amount of time to evaluate. And so then if you don't do the dead code elimination or the lazy evaluation or whatever right, then your program is an infinite loop and you just miscompiled it. So, um, but yeah, I don't know. So,
Well, sounds like you got some issues to work out.
yeah. So,
I
I
don't
mean,
think there's
that's
any
the top.
conflict here in IRs. I think, you want an IR that's close to your source language to start with, and then progressively lower it to the hardware. It's a very common compiler strategy.
Mhm.
In the case of simple, because the language itself is C-like, I can drop it to a hardware, close to the hardware IR in one step. But if I was coming from a functional language like Haskell with like laziness is built into the language, I would probably start with a IR that knew something about function calls and recursion and lazy evaluation and did some optimizations at that level before lowering.
Right. And so that's where I want like a wide spectrum IR. I want to like I don't want to have like, 10 different IR languages as I progress through.
So
I
okay,
just want
so the there's the short answer and the long answer. So the short answer is simply um, you can get these IRs to be, I want to say functionally the same or very similar to each other, but it's difficult to get that right. And then the long answer is practice, practice, practice. Write a compiler, write an IR, use your IR in anger for a while, write another IR for functional, write another IR for lower and back end things. And at some point, you should start seeing there's a lot of commonality in these IRs, and don't need to have dramatic IR language shifts. It's not required to get things done. So Simple
well,
currently has an IR that is an ideal three-address risky kind of sort of magical backend machine, and then it has machine-specific IR, and the IRs are extremely close. Just a little bit of node description, and the machine versions have a different tiling of what the ideal are for doing the semantics, but they're not being used for the semantics. They just carry encoding bits and register bits and things like that. So in one sense, it's the same IR, and in another sense, it's a different IR, but the IRs are not very far apart. Okay, can you do it with a functional recursive thing? I don't know. I certainly tried that with AA, and I stopped and did simple because I had more traction and I needed to get that done. Need to get people working on simple, thought I better pile in too. But I fully intend to get back to AA, and whether or not I do functional smart things in the same IR as the low level, I probably will continue to do functional smart things in the same IR as the low level IR. I think those are not incompatible.
okay. But yeah, I guess for me the issue is I don't really understand what an IR is because like I look at it and I see you have all these like
Right.
different
Go
kinds
do.
of nodes.
You will learn by doing. It is time to go do.
Yeah. But you have all these different kinds of nodes, and then it's like, you have add nodes and if nodes and phi nodes and
Right.
like or phi nodes. I don't know how you pronounce it.
Yeah. Phi or phi, GIF or GIF.
Yeah. So, but you have all these nodes, and it's like, well, how do I know I have the right set of nodes? Maybe maybe I don't want phi nodes. Maybe I want, conditionals or something. I don't, I mean, they are conditionals, but maybe I want case statements like Haskell instead of if statements or, something like that.
Go do. In the case of simple, it's very easy to make yet another port on purpose, and it brings these things in one at a time so you understand what piece of the whole puzzle that they're solving for,
Hmm.
right? The adds and subtracts, multiply, and divide solve for a particular piece. The if and the control flow solves for a different piece. Loads and stores solve for a different piece. You can go bring them in and say, what part am I doing here? In Simple's case, the IR is intended to be some machine goes down to some machine code, so it has to do what a piece of hardware does. Loads
Okay.
and stores, jumps and go-tos, add, subtract, multiply, divide, blah, blah, blah. That's what it does. So you have to have those in your IR.
Also, be prepared to redesign your IIR as you learn to implement optimizations, because it's very common that it is possible to implement optimization in an IR, but it's very, very painful. And if
Yeah.
you have just added one construct or removed some constructs, then it would be easy.
Yeah.
So that's a very easy trap to fall into to avoid that. Just because it's possible to do something in IR, it doesn't mean the IR is well designed, because
Which
it
is,
could have been designed so to make the implementation of optimization easy. But
yeah,
unfortunately, at least I didn't find the shortcut. So I often learned the hard way that, oh, this sucked. I really wish I had done that.
right, right. So I have that same exact story in C2 with it's SSA all the time. And then the major loop transformations that do whole block loop chunk manipulations. Take this chunk of code, which was a body of a loop, and it has 17 exits. 90% are for control flow fails that are probably never taken. But 5 or 6 users said break out of the loop, clone it, Well, the breaks would go to jumps and go-tos and whatever, and they would form out. They would merge the two different loop bodies. This is how they do this here on the screen. Get two different loop bodies. I got like three outs of here and three outs from here, and pairwise the outs need to go into different places and merge. I exit in the first iteration. I exit in the second, or the even iteration. I exit in the odd iteration, and they would merge and then carry on. And then lifetime analysis would say some things were live up to the first point, but then dead, or some things were live down to the second one, and I had to have it available for the second one and not the third one, except in the even the odd versions. That amount of manipulation to get that correct turned out to be quite a bear in the raw C2 IR, and a strong competitor, which I didn't implement, but I stared at it long enough to think about it hard, would have been to come out of SSA, clone the loop body, go back into SSA. I did the hard thing, which involved following immediate dominators up and down every exit path to find the nearest and closing merge point for the two different exits, which now, in a prior exit, there was exactly one point you went to. Now there are two that had to merge. Where was the merge point and what was the lifetime? What fees were needed at this merge point? What was the live across that point to fee there? That information was not kept in the C2IR sort of on purpose, very usefully up until that point. So I did it the hard way. C2 remained sort of super fast doing these things because of that. But I burned a lot of engineering cycles on that. And, it's a reasonable argument made that it wasn't the right IR for that level of thing.
So is there an easy way then?
There's no easy way. You get a bunch of bad choices. My other bad choice was come out of SSA. That's not so easy. Do the thing, which at that point would be easy because you were now in classic control flow graph. Then go back into SSA because you had a bunch more things for which SSA was the right answer. So going out, doing, and going in, the doing is not easy, but the going out and the going in are not. And so I never did it. I didn't, at least not in C2. But, I had to eyeball it pretty close. It was like, not sure which one is the right one here.
Okay.
Well,
I think that's a good time for me to leave when you're talking
Okay.
about going. Goodbye.
Enjoy your music festival. Yeah. Bye.
Yeah.
The discussion previously kind of reminded me of a JIT that I briefly looked at some years ago. Higgs. This is a PhD project by Maxime Chevalier-Boivet from 2012.
It helps if you have links, if you have something specific,
Yeah.
but finish your conversation, but see if we can get a link into the doc.
Yeah, I will. But it's a JavaScript JIT, which is I think they ended up going like basic block based, very heavily tracing JIT, where essentially every single basic block is JITted for the types that it currently has. And then they gather data because in JavaScript, like every expression, everything you do will have a lot of type assertions or type checks built in kind of.
Right.
So they would gather all of that data, and then whenever you're moving from a basic block to another, you would check, what guarantees do I have? And do I already have that next basic block JITted for these guarantees? If I don't, I'm going to create a kind of strong version. So it was a fairly interesting one. I believe they also used a split stack system where they had like types in one stack and then the values in another for some reason or another. But I was kind of reminded of that, and it's actually it didn't quite die. The Higgs project doesn't live on, but YJIT for Ruby is being built by the same person, I believe, mostly using the same ideas, principles.
Right. Yeah. C2 certainly does various kinds of specialization. So that was running around like JavaScript has it in spades. It just has to do it in bulk. C2 definitely does things where it knows something about a type and then chooses to inline or not. And suddenly you get a variant version, whatever, that's known to be this type or that type when he starts going inlining, and that turns into better things. But it wasn't the focus. But yeah, watch the JavaScript guys go down this path. I think it makes sense, actually.
Yeah, I was just kind of looking at one blog post by this person, and they kind of mentioned that their idea here, one of the ideas anyway, is that uh, if you kind of maximally type trace and JIT this way, at the end of the day, your interpreter won't matter anymore.
Yeah.
Which is it's a fairly interesting choice. Probably makes for relatively fast code as well. Though I don't know if they have like loop invariant motion and so on, because like if you're basic block-based jitting, how are you gonna slot that in?
That's a good point. Like the usual trace jitters go into the hit a back edge, and then they have a loop, and they do loop things on the loop, and you have one exact loop, and it's exactly this trace on the back, and all the exits don't count when they but then they get loop invariant code motion on the trace. Okay. Yeah, basic block of time, I would claim you'd have issues with code bloat. Yeah, I cache bloat.
That was often the theory of a tracing JIT, was that you could have any arbitrary interpreted anything, and eventually you would get performant code out because you just figured out what were the unnecessary parts and just kept boiling down the stuff that was hot. In theory, a tracing JIT should need to know what language is running on it.
The experience I have says that it never quite beat a method JIT that's been done well, but all these things are like straw man typically. This version or that version, I did mine this way, you did yours that way. And I did a straw man of yours and you did a straw man of mine, so we could have apples to apples comparisons, except they weren't because each of us had a straw man in the other direction.
Right. What you really want is projects that have lived for a long time and see how they do. You know, the JVM has lived for a long time and gives us an idea of what sea of nodes can actually do. And the Pypy JIT has lived for a long time and people put a lot of effort into it. And I think that's the best example of where a tracing JIT could get to.
Yeah, and then the funny difference there is Python versus JVM bytecodes. Right? The JVM bytecodes are strongly typed from the get-go. And out of that comes this notion that I already know all the types going in. And there's no places where you flip accidentally types from int to string to whatever because of some auto conversion happened.
Yeah, that's the big difference. Python is strongly typed, but it's strongly typed only at runtime.
Yes, yes. Right. And the static typing means that I have large regions of code for which the types are all known when I go compile directly, as opposed to ones where I have discovered via your type assertions as you went, and then I have every possible bailout path for when those fail. So I don't know, in my head, that's still not a fair apples to apples comparison between Pypy and the JVM, because the source language they're dealing with is substantially different.
Pypy also landed in a particularly weird place, which was there was a cultural mismatch between their tool and their community.
Oh, really?
So the culture of the Python community that grew up on CPython is do fiddly, complicated logic in Python and do hot inner loops where you just need to crank through a bunch of matrix algebra by calling out to native code.
Yeah, right.
And so fundamentally, Pypy was trying to solve things like matrix multiply very well in a community that had decided anytime that was the actual problem they had to call out to native code and not do it in the VM anyway.
Right. Yeah, I watched that.
So to some extent, they were trying to optimize a standard library that was trying to optimize for a thing that behaved very differently than they did.
Yeah. I have looked at, and there's some nice posts from the Pypy folks about the set of things that they do differently or they think they need to do differently in order to get performance out. It's not a big list, but it's low-level things that, Python exposes whatever it's going to expose that you would like it to not have exposed. And most people don't rely on it, but some people do. And then it breaks these some people's. And if if you have to have this thing, then you can't do a bunch of optimizations for whatever reason. And they're clear. It's like 4 or 5 things. It's not a big list by any means. But yeah. And I think they voted for performance and don't do these stupid things. It's like Java finalizers minus or something. Don't use finalizers as your way to do any go-to-ish kind of whatever, because never mind. Finalizers are a bad plan. Different. Okay.
Next topic.
Yeah.
Hmm.
Let's say I have encodings pulled in, but they're not running reasonably. I don't know, you're the and how are you handling this kind of portability to this kind of compiler thing? Is that of interest? Since I can't run anything, I can only show the design issues.
I have one question for Simple.
Yeah.
So in the checking that the optimizer missed some optimization, there is a break here for bug.
Yeah.
Like print statement. How do you orient with that? You can share your screen, because if I share mine,
yeah, that's a debugging tool for a common
yeah,
problem for which
because well, when I finished the chapter 12 and I fixed all the things, there was one mechanized bug in chapter maybe 11, and I triggered that bug. And when I break for exception, then how do you orient around the nodes to see which optimizations were misplaced or missed?
Right. There's a strategy that place is intended to be a convenient strategy for solving. Let me go to main on simple here and fetch. And I'm rebuilding. So IntelliJ, wake up. I just changed. You have not woken up yet. Oh, it's because it's wrong chapter. No, why are you still here? Hang on. Yes, I'm IntelliJ. Emacs like fucking doesn't care. IntelliJ does.
But in order to trigger it, you have to have an example for break here for bug.
Right. No, I'll force an example in a second here.
Okay.
And I have to set my view to be double size, and I'm trying to get the change which. Okay, there's that. I'm rebuilding. Let me hit the share and I'll finish. But I'll break something on purpose and then come back around and see if we can't hit it here. Let me run it once, get a debugger going, and then I'll go break something here. So I'm going to go off to Emacs and build my chapter 20, and then I'll go break something and see that I can find out who discovers the breakage, and then I'll work you through what I did. Okay, so chapter 20 is alive and well. Nodes. Okay, so somewhere in here, I'm going to take an add dep out. Add dependency. So the common failure mode is add dependency isn't happening, and then you fail to catch an optimization because you add dependency should have been there. So I just took a random one out, and this one is going to not fail. There you go. That's excellent. Let me try taking a different add dep out. Here's the IDOM related ones. Those are more obnoxious. He's like, it's all good. So many add deps have been added over the years. Yes. How about this one? And a lot of these I don't have tests for directly because they just came out of a buzzer.
Yes, for me specifically, that one produced by a fuzzer, maybe in chapter 11, is the only failing test for the whole.
If you have a test case in hand and you can dump it into the doc, I'll pick it up and see if I can trigger. I'm on chapter 20, which has a bunch of other fixes put in. So
the problem is in my implementation, because all the tests passed, and only the fuzzer test, one of the case of the fuzzer failed. and there is revealed you can break there for bug in order to start debugging where the tests went wrong, because there is a problem in the implementation.
Oh, you know what? I wonder if I've turned it off on this guy. No, there he goes. Okay, that one went way too much. Okay, and okay. I have a failure by cutting off all of them, all of the dependency addings. Let me go see who does it. Chapter 18, function 9 is the sort of first one here. Okay, what do we got? I got that I have an open window in Emacs. Go again. Yeah, no, not this one. Okay, break here for bug. This is what you're hitting, right?
Yes. Okay.
Yeah.
So
go ahead.
Yeah, go ahead.
Okay, so I want to show what happens here. Okay, so that only happens because I'm in the Octo pass doing iterate on the main work list. So this is the main, do them all until you're done. There's an assert that it's clean on entry, and then you ran a while and you crashed. So the couple things to do here are, I have a count, that's this count, that is deterministic, so I can break point right beforehand. I have at the failure point what failed. So what I see here is that something in here failed. This is usually either the is a test failed or the peephole failed, and it's often the peephole that failed. Oops. And it means that it was able to do something with an item that wasn't on the work list.
Yeah.
Okay, and that's the failure. You should have been on the work list if you could do something.
Yeah. Yes.
So I need to know the original guy that's in, and his node number is 43. It's going to be the same guy at the end. So I'm not sure what thing happened here. One of them is he went backwards, and that's not going to be what happened here because I just did dependency hacking. So this assert is fine. This one is you're one of the early primitives, or is keep means you're in the middle of parsing, and the parser isn't done with you. So I don't care what happens there. The parser is going to hack you some more. But then it's, you're on the work list, get out. So you are not on the work list, but is able to do something. And now I don't know what happened here. This people did something to end. I only have the post state, and I don't know what he did. So it was unclear to me why I got here, but he was able to do something, and he shouldn't have been able to find it. So what do I do? So I'm looking for 43 makes a change on iteration number 6. Oops, iteration number 6. So what I'm going to do is I'm going to rerun. I'm going to set my count here to 6. I'm going to stop at the people and say why you did something that changed the graph such that this other dude, 43, should have been put on the work list and didn't. Why? What did you change? So go inside and start looking here. First, I'm going to look at the type computation. It's old versus new, and get rid of the IntelliJ's infinite yellow box. It says types didn't change. Hash is 0. I didn't find you in the hash table. It's a cast node. It kind of makes sense. Idealize on a cast. So the cast says, I did a type thing. I'm going to discover, okay, the type I have right now is some TFP, and I'm about to compute an input type from my constant, which is going to be type, anti-TFP. That's something impossibly high, probably because dead code says you can't get here. But he's going to say, because of that, I'm going to return N1. Okay, that means this cast is useless. You are definitely a function pointer from int to int or higher in the lattice. So it's not necessary to cast you. The cast would be an error if I didn't go look here for a second here. Cast is an error if it's not removed at the end of the optimization. That is, if I can't prove the cast is useless, it's an error. Okay, so this guy is supposed to throw on me. I don't have a test case for him, so there you go. So I did something here, and this means I removed a node from the graph. I'm about to remove a node from a graph. I got a node. I'm going to report progress. I'm coming out here. I have progress. I'm going to say this thing is now going to be removed. So I'm going to walk along here and see if I need to update your types. And x is unequal to n. No, it's the same thing, or some constant. So something happens in here. It's time to go. Time to go put all my neighbors on the work list.
Mm-hmm.
So the output of the cast goes on the work list. His outputs are some call, probably the call that's ahead of the call end node that we're curious about. It is.
Mm-hmm.
And I don't need to do, oh, and then I don't get the, where's the add depths for this guy? That just says put me on the work list. That's not the issue. I didn't change nodes. I don't have to do graph editing. Oh, here it is. Then I add dependencies to work list. So what's the dependencies on the call node, on the cast? He has no dependencies. The array size is 0. He should have had a dependence. So somewhere in here, when I have a cast that's making a value that goes away, my expectation is something else happens that should have been put on the work list. So I understand that the cast is not going away. Why is my call end changing? So let's go discover that one next. So between those two, we should sort out what's going on. So here's the progress on work list. This guy's running it walks the whole program, so I'm just going to stop it at the point here and say, what did you do? Well, I know his types were okay. And it's this peephole that did something weird. Let's go look at the peephole here. His old type, new type, these are going to be like unchanged. No, yes, okay. So his type's changed. So the cast went away. The cast also lifted type values to an impossible higher than the centerline functional type, which typically means the code is not actually executable. So when I would call the thing using the function pointer I have, the return of the call, the fact that I would go into the call at all is now in question. Like I have an impossibly high type. It means you can't get here anyhow. So I should be able to go into the call, but it also means that the call is acting as if he's not reached. So instead of returning an int, he's going to return a twiddle int. He's saying basically my return value went impossibly high because my function pointer that I'm calling, the call and the function pointer went impossibly high. So I'm going to ask a question here and say no on this part. We're going to idealize. Now I'm into this guy. So this is still me asking the question, why did call in care that the cast got removed? The cast lifted and got removed. Why does he care? So he says, no, here, why did that not blow up? Oh, the type change. That was it. It was just the type change. I claim that you can't be reached because your type is too big, too high. Not too big, too high. Let me go get you the other piece here, which should be like, see if this functions. This has been broken on and off. Oh yeah. Is it here? No. It's code desktop. Actually, probably just do code. So here's the function. Here's my one function. Oh, there are two function pointers. Here's a cast. The cast went to impossibly high. It's probably not reachable is the issue. Whatever 56 is, his control claims are reachable, so that's not the issue. It's 56. Where's 56 in here? It's an impossible number. So some other constant folding happened, declaring the cast is unreachable. I'm making the call. The return is now going to become, since I can't be called, the return value went to high int. In a minute, it should go to dead control as well and say, this path is not reachable. So something's happening here that's in the middle of folding, and it's here. This is part of it. So the test says, do I have a function pointer? Is the function pointer null or not? Well, it's impossibly high. It's above null. So I shouldn't be reachable from here either. So things are mid-collapse. There's some disaster happening to the program, and he's mid-folding him up. And then the call in changes types based on the function pointer. Well, I know for a fact that the calls input for the function pointer brings in the return type for a call in. I don't know what the function body looks like. I don't have an example of function body. I have a signature for the call. That signature includes the return type. So in the absence of other information about what it is I'm targeting the call to, I'm going to claim the return from a call end is the same as the return type from the function signature, which is twiddle in. So this is not a neighbor. So call in depends on the function pointer's return up here. So that's a two-step remove. That means I need a dependency. I turned off the dependencies, so they're all busted. So that's fine. So that's broken. So he should have had a dependency that says, when this type changed, this type changes. That's what I was missing here. So, zooming out, well, how do I do this? So I hit this breakpoint. I gather what is in and what likely changes happen to it. Sometimes I can tell what the change was on in. Sometimes I can't. In changed. And probably people changed in. And if it returned me a new in from the old in, then I can't tell by observation on in itself. But if I get a new in that's different from in, I can probably look at the in and say, something happened and I got this other thing. Okay, maybe I know, maybe I don't. Fine. I gather this. I go up to the top. I gather this. Now I'm deterministic. I'll just go again. I set my breakpoint. The breakpoint says stop. I look through this optimization, this peephole. He changes something such that the in down below had an opportunity, so he needed dependency. And that's how I sort those out.
Tricky one, because the source of changes aren't exactly...
Yeah, right. They're nearby. The point of the dependencies is they're not adjacent, but they're generally nearby.
Yeah.
If it's adjacent, then this one did it already because I just walked all the neighbors and said done.
Yeah.
Right? Okay. It turns out if you change something hard, you get this one, which is the inputs walk all neighbors. So those don't need dependencies. But everyone who's 2 steps or more away needs a dependency added. And that, that's what happens.
Okay. Cool. Thanks.
Yeah. And that particular fail happened enough. Now it's not. It happened enough that I left a permanent infrastructure in place to diagnose those. Like I had them on and off and I was hitting things periodically. And then Amelia, hey, see you, Derek. Amelia did the fuzzer and the fuzzer found bajillions of them. For like 2 months, I was fighting those things, every other day. And it slowed down finally. And then I put the fuzzer hack into the make file directly and it kind of picked up again. And then it slowed way down. And now I don't find them hardly ever. I think it's done. Like there's only a finite amount of code. Only a finite number of these things can happen. So I think we're done for the moment till new optimizations show up. We're done for the moment.
Yeah. So my conclusion would be that I believe it's almost for sure it's impossible to exhaustively check all the combinations of all optimizations because they're kind of loosely defined in terms of each other. Let's say if an add node in idealized section, then it describes how it interacts with other nodes to conclude its optimizations. So they're locally, as you were saying, 5 years in this podcast. So they are locally and isolated, and they only calculate their changes in terms of other nodes. So it's impossible to approximate the graph to such precision that you can conclude that one optimization is happening, but it's not happening, but it should. And
here I'll disagree.
Yeah,
the peepholes are typically small and local, and therefore it always suffices to read the peephole and put the local neighbors on the list.
Okay, I agree with that. But how you end up with interaction optimizations that you somehow end up with a broken graph?
Because it's local. The only the dependencies happen are all these local things. This is a case of it doesn't matter. The point of this is it doesn't matter what the rest of the graph looks like or does or how it changes. Locally, at any given local spot, I can say, if I mutate the graph here to make a new one here, I can look at the local section and put the dependencies on. That's it. I'm covered. That covers the, whatever changes happen there. All changes are, in this sense, all changes are local.
you are able to make the optimization because you restrict that optimization based on the conditions. So you need that node, and I know what the semantics are, and I can cobble up some optimization. Yeah.
Right.
Okay.
Right.
And that way,
So for optimizations that are non-local, then it gets trickier to diagnose them. So and there are a bunch. AdNode is a fabulous version of that. But so some of the other guys. So here, out of a zero, his node dependencies is all completely local. Find a dude who's more non-local. This is add of self. This is canonicalizing left and right. So I have ads and non-ads in a certain order.
So for curiosity, based on our starting conversation with Alan, could you introduce a node that can, let's say, it would be a commutative node, and it can encompass all the nodes that it doesn't matter in which order you put in, and you can abstract all over the operations you can. So you can do such optimization, but is it beneficial to do so?
C2 does it actually, and Simple did not. It would be change add node for add extends commutative node, and multiply and or and XOR all extend commutative.
Yeah, right? You can isolate all the logics in one commutative node.
Now the deal with commutative is that it only shows up in a handful of places that I care about, and here's one of them. If I have stacked adds or stacked ors or XORs or muls, I'm moving things around so that I get all the adds together so I can have a left spline layout of adds so I can swap them so I can get to this operation, rotation, where the goal is to get all your constants in the same place so you can fold them up. And then you get this spine comp. This is me rotating you or not. Here, I start to get a little further afield and it gets more complicated, like phi-con. What is phi-con? Well, a phi of a constant. So look, comment here, add of a phi of a constant. And I'm trying to decide if I'm going to pull the constants down or push the add up through the phi and then add the one. Take the add the one set of constants to the other set of constants, or this set of constants to the one constant. Like add one, but on the phi that I'm merging, add one and is a phi of some other constants. I push the add around. So I'm doing a rotation on a small area of the graph, and in phi-con will have add depths in it. Here's an add depth here. And this is another one, like I have this, add of a con of a con. I'm going to rotate, so I get add of con plus con, and then I can fold the cons.
You're not sharing your screen, by the way, if you're trying to
I'm not. Oh, shit.
Yeah.
No?
Oh, thank you. I'm sorry. I should. I'm here. You're highlighting and poking, and yes, okay. You got to tell me these things because it's all obvious on my screen.
Yeah.
Yes. All right. Roll through things for a little bit here. I'm looking for add depths. I'm in add node, and I'm doing add node things.
Yeah.
And a lot of them are completely local, so they have no depths because they use the neighbors to do them. But I'm trying to say, when I do things that are far afield, I have to have a larger neighbor space. But the main feeling is that all of the tests are typically small and local. And therefore, I can only impact local things.
Yeah.
So that's the reason I don't care what the rest of the graph looks like. This is the entire reason that this strategy works.
Yeah, I agree with that. So the changes are concerning only a node or two, and that is why you are able to do them, because you can pin down what their interaction can be.
Right. Yes, it's a local interaction. So here is the what I was just talking about, the add of con. Do we have add of a con plus a con? Rotate the adds so the two cons are together, then fold the cons. It's pretty obvious, right?
Yeah.
So I asked the question, is the left-hand side's input 2, so this is an add, and this is an add of this whole thing here, the left-hand side. This is the left-hand side, and this is the right-hand side. Is the left-hand side's right-hand side a constant? So left-hand side into is constant, and right-hand side is constant. Do the rotation, and then another optimization will fold up constants. I'm not going to fold them up here. I'll let someone else do that.
Yeah.
Okay. Because this is one step removed, the base expression starts from here with this little plus in the middle. And the two neighbors are an add here and a constant here. But I have to depend on this also being a constant, which makes them 2 steps removed. So as soon as I say left-hand side step into, I went 2 steps. One for left-hand side. Here's the second step. Now I need an add dep. Failing to put this add dep in, the fuzzer will catch me at this and say, hey, you didn't fold this.
Yeah.
Okay. So that's the reason the add deps are needed is so I don't have to have add deps everywhere, and I only need them when you're 2 steps. But then the complication is you have to walk through, and everywhere you're 2 steps removed, put a dep in.
Yeah.
So the boilerplate engineering coding issue is it's easy to forget add deps, and then they show up later in this. Hey, look, I missed an optimization.
So add deps are like a promise in order to continue the optimizations? Or...
Yeah, the add dep says if this thing changes, go rerun this pointer. And really, this is not necessary unless you failed here. So if you're a constant and the right-hand side is a constant, you didn't fail. You're going to do this, and I don't need the dependency. But to do that little deeper thing, I need a more complicated test. It says if all the conditions are correct except for this second guy is not a constant, then add the dependency. But if all conditions are correct and the second guy is a constant, then I go ahead and do the transform instead. Don't add the dependency. So here I'm adding the dependency even if I do the XForm or not. But it turns out add dep's pretty cheap. And I'm probably going to add a dep there anyhow for some other reason. So I don't care. Fine, I did it.
And fees are more complicated. That's why they have to.
And then we can go look at fees. Yeah, fees have their own, remote.
So one thing I would like to point out is if you can
go back to the add.
It's a cool way that when you say the node in 1, 2, 3 or any numeric, it's a cool way to isolate the context. So in any number, it's a interesting way to the nodes are like the context, and you pull out any node, the first, the second, or the third. So you pull that like from the context. It's
okay. Let's talk about this. Gets into how you talk about these things on a regular basis, because I have lots and lots of them.
Yeah.
So way up early, I said in one to get a left-hand side out. And a right-hand side out. Hey, do you understand this context? Is this not clear?
I understood them, but I was just pointing out that an interesting way to represent, to pull things out of the context in order to isolate them to be amendable for optimization.
Okay. What you say interesting? It sounds like you think you have a better plan.
No.
Oh.
I'm thinking. Can they represent in another way?
Right.
But there's typically not much. We can represent. Scala can, for example, let's say pin down if you pull one in one, for example, to know that it's always the control node, or what was the zero?
Yeah, I have shortcuts for those kinds of things in a bunch of places.
But essentially, the variation is so high that you have to cast. So you cannot approximate all the things inside the number. You have to know what you're dealing with. You have to cast it because you know that this is the case, and consequently you have to put a test that you are sure that this is the case. So
control node is a very common thing in slot 0. It's either null or control, almost always, but not always.
Yeah, but
because it's almost and not always, I can't get strong typing out of an array of nodes. And I frequently do for all inputs or for all outputs. So I like the array notion. And then I fairly frequently do I know it's a control. And I can go pull out things here. One or more of these cast guys will do the control guys, probably just from CFG node here.
Java cannot approximate that. So you can, for example, you can approximate that with a Scala a heterogeneous list, because each node element will be its own type. So you can encode the notion that the first node is always the control node. But what if it changes meaning it's not always, then you lose that.
Okay, but I say it's not always.
Yeah.
Yeah. There are definitely projections. You typically use their slot 0 to say, I am a slice of a multi-part value, and I just use it on slot 0. Now, if I move a projection over to slot 1, and he says my slot 1 points to my parent, which gives me the multi-part, and I'm a slice of the multi, then I can leave slot 0 as control. But slot 1 is variant for everybody for different reasons. A call and a call in, not a call end. A call in, slot 0 is the call, it is a CFG node specifically, although it's a call node.
Yeah.
So that is me saying call, which is a specific class of CFG node. So it's even more precise than CFG.
But
and I use this call all the time.
Essentially, you have to dependently type what the meaning changes based on the node. So yeah.
So if I go to call node, not listed here, well, it is listed here, mem. Oh, I'm not even using this one, but mem is always in slot 1. And memories and then function pointer is the last guy, and this will be something that computes a type function pointer eventually. And then the arguments are in the middle.
Yes.
So the argument index here.
So my point being that there is Java. If you have more powerful type system, then you may be able to encode more type safety inside the calls. But I'm not sure is it really worth it. But that's that specific piece complicated things, because you have to really internalize them in order to get what they mean based on their context.
Yes. So calls. So I do try to lower the count of these unique things. So everybody who takes in a sort of standard execution semantic will have a control in slot 0, a memory in slot 1, like returns do the same thing here. And a value in slot 2, and maybe several values in 2 and up. So again, control in slot 0 and memory in slot 1. And then for returns, there's one value only, like arguments to a call have as many, but returns only have one. But he needs a return pointer, return PC. And that's in slot 3 now. The new allocation is a particular version of a call. It takes the size of the thing you're computing and the type of the thing you're making a allocation for.
All the thing changed based on the on what you are really talking about. So that would be hard. So approximating the runtime types of the graph would be hard to next to impossible, because there are so many things that are encoded like one type.
That was the decision I came to some time ago. I would really have liked to have had that typing. I couldn't figure out how to get it in any language.
Maybe for a future I will try. That was my idea. Somehow encoding more type safety when you know what you're talking about. When you pull it out, and it's immediately, you don't need the cast. So it's not really. If there are lots of things, then maybe the type system can help you figure out that you're doing something that you're not supposed to. And but the flip side of that would be that you if you master that craft, you know what to cast the node, you know what you're expecting. So it's
like 50 guys in here. Although add-f should only have function pointer and a floating point computational nodes, but that's a weird set.
Yes.
And constant's pretty generic. There's a bunch of integer ops, add, and whatever, that know they only compute integer things. Mem merge only merges nodes that are known to be memory type. This is kind of a lie. There's a subclass, scope, which merges anything, because it's the parser scope value.
Yes.
The lexical scoping during parsing.
Yeah, so most of the things deserve their semantic designation in the node graph hierarchy. One interesting thing would be why it's beneficial the type to be it's a node subtype, not all the nodes that have the content type itself. For example, let's say the Scala allows you to define a type something inside a class. So it has to be represented like a differently because does it deserve really for a node type to be a type to be a subtype of the node to be its own separate thing? So you have to be able to reason about it inside the graph.
Sorry, I have nodes that
Yeah.
are subtypes of nodes.
And the type to be a node, to be a
Oh,
subtype
the
of a node.
type.
Yes, yeah.
Types are not nodes.
Yes, they're always inside, but always inside a node. Yes.
Well, that's no, they're carried outside nodes all the time. There is a type field on the node, no
Yeah, yeah.
question.
So each node has its own type. So
Each node
yes,
carries a type.
carries the type. Yeah,
Constant carries a second type field because he carries the type that his constant is versus the computed at runtime type, which isn't a big deal except during the reset of algorithms. The reset happens on the main type for everybody differently. But if I'm like a function node, his type is control. Am I executed or am I not? But I carry a fun pointer signature that tells me what does my function signature look like? So he carries multiple types. And then the compute call, everybody on the planet has a compute call. He inherits his, so that doesn't help any. Everyone on the planet has a compute call, and then they compute all kinds of types in here. So these types are all outside of a node, and they're just in the local, local variables while I'm deciding, I know something about this minus node.
Yeah. So the observation I made here is that the IR is specifically geared towards that it's representable by a CPU at the end, by instruction, by something concrete that can be executed.
Right.
Yeah.
That's yeah.
Yeah.
So like in other worlds, I wouldn't need a shift left and a shift right and a shift arithmetic right. I would just compute these from various combinations of ands and ors.
Yeah.
Except that these nodes all appear as for free instructions on every CPU platform on the planet.
Yeah.
And are useful in various kinds of bit field manipulations, which are useful for people who have, memory size, and I want to encode things as bits because that's what I'm going to code them as, and then I'm doing bit fields with them.
And the complication would be if you pick an IR, and we were talking with Alan, if you pick an IR that is not easily lowerable or exactly representable by something CPU, you have to come up with that. Let's say we define the type to be a subtype of the node, and in the end, you have to have some representation for that if you intend to emit it in the program in the executable.
I have that going on right now where I'm debating the value of bool node and deciding if I want to do something about lowering it in the IR. But bool node produces a 0 or 1 semantically.
They can be represented as integers. So yeah.
Yeah, well, and then it's represented as an integer versus a Boolean. That's a separate problem. This one is the bool node is usually followed by an if, but not always, doesn't have to be. When I go to the code generation, the encoding side, a bool, which produces a 0, 1 followed by a jump instruction, wants to normally be folded up into a compare and a branch. And then you get the flags is hiding in between, and you never manifest a 0 and a 1. You manifest a Boolean flag in a 1-bit flag register. Right. So the IR then, let's see if this guy will let me get to chapter 21 here. How about you? Go to chapter 21. Leave my change. I actually don't have it. Wait, I did stupid changes. Let me get rid of my changes. These are all me hacking out. Discard all changes. Thank you. Okay, now I'm going to change to encodings. My chair just got itself unstuck. Okay, are you going to let me find chapter 21? Yes. Okay, so go to, all of them have the same problem here. Here's fine, and now go find me set Z something here. Yeah, this guy. So when I'm walking the IR to convert from ideal nodes to machine nodes, I have this funny situation where when I see a Boolean and I'm going to do the conversion, I stick in a hardware compare to get a 0, 1 in the flags register. Then I set the set instruction in who's going to manifest a 0, 1 and a standard GPR in case you wrote code that says if A equal B plus C equal D and you turn it 0, 1, so you can just add them like integers, or you're going to store them as a Boolean value somewhere. I need a Boolean value. Can't store flags into a field. I have to have it a Boolean value in a register to store to memory. So somewhere in the world, I have to have a way to make a Boolean value. But it turns out everybody who does test and branch, which is 99% of them, produces the set flag because the semantics are bool node demands a 0, 1. But the compare here is going to put flags on. If I follow it by an if, the next thing that happens is I throw the set away and I just want the flags. Where's the, let's see here. Where's the example? And where's my jump up? Post selection, instruction selection. If I see I've got a set and he's a set of a compare, bypass the set, which makes it go dead. And I make a set instruction because my semantics of my ideal IR demand a 0, 1 in our general register. But the 99% use case is, you don't actually need the 0, 1. You just want the Boolean effect. So there's a mismatch. That mismatch causes me to have to produce code to produce a 0, 1, even when most of the time I don't care, and rarely, like I could have delayed the issue of a set op as an optimization that said, I know that the user in the Java land said, if some Boolean thing, pick a 1 or 0. And I could implement it the same way. I set a little control flow diamond. I optimize it to a set instruction to save my life or whatever. Coulda, woulda, shoulda done that. Instead, must have had to, before I could compile any fucking thing on machine code, implement a setx op, which I didn't throw away. So that's the difficulty of having a mismatch between the IR and the low-level hardware.
Yeah. Okay. Cool. Thanks.
Yeah, right. So now do I care about bool? Whatever. I might, the C2 actually, I knew that I had different hardware ops, had different notions of what flags meant and how they did it. And I did a three-way thing. I didn't like having a three-way thing for complicating my life elsewhere, but it simplified my life at CodeGen time. And the three-way thing was I had a Boolean test that then could manifest to something in the flags that I didn't jump on, and the flags and jump would be in one spot, or the manifest into flags is one and the jump is the other. But I had 3 ops in the ideal IR, and the typical encoding scheme would grab 2 and 1 this way, and a few architectures went 1 and 2 this way. And it was kind of obnoxious to have a 3-way thing floating around in the ideal IR. So now I have a 2-way thing where I have a bool and an if. But then when it comes to encoding time, the bool has to produce a 0, 1, which the if doesn't actually want the 0, 1. He wants just the flags effect. So when I go to encode, I actually split this into the 3 parts. It's 2 parts out of it. I can't show this on the camera. This splits into 2 parts. Then the jump says, skip the middle part and just get the other version. That's all I want. Unless you're using the 0, 1 effect, and then you get to keep the 0, 1 effect. Yeah, fine. And this same split happens on all the CPU choices. RISC-V and ARM have the same problem going on because it's not a good fit. Yeah, so comp says something about do a set on a bool, but then the jump here, I believe, go find out, it's called something different here. Maybe it's called branch. Says, he doesn't have it here. Maybe RISC was the one that, no, RISC is the one guy that does it. He doesn't have flags. ARM has it. So RISC did it the way the ideal IR does it. It's going to be ARM, which is going to have exactly this problem. Yeah, ARM says post select if I see a set op, just skip it. I don't want the set. I want the flags. ARM and x86 have flags. They don't need the set. Risk needs the set. He doesn't have flags. Fine.
Yeah, small subtleties between.
Yeah, it's just interesting. Well, all your design choices come back to bite you in funny little ways.
Yeah. Because you're trying to push them on a different hardwares, on different ideas.
Yeah, with different notions of how things work. That's one way risk varies from ARM and x86. They have other ways they vary that cause you to have other matching issues. The matcher here is walk the ideal graph. Here we go. And then make some decisions. So I come over here. Here's the list of ideal nodes. And I switch on them all, however many there are. And some just are carried through without modification or change. But most do a little minor thing. A lot of these do little minor things. This is a carry through, no change, carry through, no change. Minor change, minor things. But then, everybody involving loads and adds and memories and storage on x86 do crazy, crazy things. Like here is add on an x86. It's giant. It says add of a load. Oh, I can pull from memory. And then if the reversed, swap sides, I can do an add from memory if I have the load the other way. I didn't implement that one because no one's hit it yet. And here I have an add of an immediate, and it's fancy enough. I'm going to go do a Leah op, or I have a shift. I can do a Leah, load effective address. Otherwise, if it's a 0 value, it should have been this one should be an assert because the optimizer cleans those out. That shouldn't happen. So that was Tommy didn't understand what you could trust out of the optimizer. So I should change that to an assert. It can't be 0. But you do a small add. Although there is a size check, it has to have happened already, or we're missing it. We're missing the size check. Yeah, there's a bug here for size checks. And then there's a Leah that comes along. And Leah himself says a bunch of things, including scale, base, this, that. Oh, this is main. The main? No, it's chapter. Oh, I thought I pushed this on the. I thought I changed it. I thought I fixed that already. Okay, fine. It's x86 will take an int. You can't have a long. You're supposed to have a test that says, don't go here and use the whole giant 64-bit immediate. If you have a 64-bit immediate, you're going to add to. Fine, whatever. Anyhow, just saying add has 200 things on an x86 and an ARM and a RISC add is, pretty tight. And again, for like add immediate versus and actually RISC and x86 are kind of similar here, other than the range of the constant is varied. This is missing. Where I did the change here. I'm missing a change in all my back and forth and back and forth. It's fine. All right. Anyhow, I was hacking this morning and I cleaned out some of these issues, and I'm seeing more issues having to do with range checks on the size of the integer immediate. Like you can't do this with a full 64-bit immediate, but type integer will produce a constant 64-bit immediate. So you can't do the and with a 64-bit immediate that's big. And there should be a test here that says and you're an immediate 32. And I just hacked immediate 32 in and pushed that. And I'm not seeing it. And so why am I not seeing it? I thought I was just here on the current branch history, like I lost something. Is giant. Oh, you know what I did? I pushed it. We'll have to see now. Oh, geez, it could be a merge fail. Fucking A. I merged from Tommy did all his stuff in a side branch because the main branch was being used for register allocation. And then I started down a encoding path, but he was doing the encodings and I was doing register allocation. So he went into a side path. So we merged this morning. And then a bunch of changes I put on the side path, like after I knew what the encoding API was going to look like. So how do two people work on some type code that they share common things? But some guys defining the API, the other guys using, there's a mismatch. So I changed his API and then everything had to be touched and use the new API, fine. So I touched that and merged them. And now I see a bunch of changes that I did when I touched all his encodings, included a bunch of safety checks I added and I merged. I'm not seeing them in the merged answer. So I'm going to yell at, GitHub for failing the merge, Git for failing the merge, or throwing code away, or I'm not a Git expert. Now I'll sort on it later. Fine.
Yeah.
Okay. Done,
So,
done. I'm rambling on. People are walking away, and we're
yeah,
basically done here.
yeah, cool.
You want to do your merges locally and then force push. That's the
Um,
answer.
yeah, probably. You know, I did a exactly. He did a pull request on the chapter 21, and I went on to GitHub and I did squash and merge. No conflict, squash and merge. Okay. Now I'm seeing a bunch of shit missing. Fine.
That's unfortunate.
Yeah. Yeah.
Git has a habit of punishing you when you least expect it.
Yes.
Mm.
Yes. It is the worst of all possible source code managements I've ever used. In my life,
Except
I've
for
used
all the
quite a
rest.
few with quite a few big teams. It is the worst one by far.
I disagree, but I understand where you're coming from.
Okay. There have been worse. I have certainly used better. How about that?
Well,
Fine.
it's pessimistic versus optimistic, and for concurrency for large distributed orgs, Git's the only choice. But for
Yes.
small teams, Perforce would be
I mean,
better.
Hotspot, the core VM team was 70 people, and we used Code Mangler from Sun, Code Manager, Code Mangler.
Yeah, but they did switch off that and switch to Mercurial
Yeah.
after
Then
after you left.
other projects I've used Perforce, for which
That's a good
I
one.
found Perforce just fine. It worked
Yeah,
great. Fine.
that's the only commercial one I'd ever consider using. It's good.
Perforce, yeah.
Yeah.
Yeah. All right, fine. Done. I guess till next week.
Yeah.
I will see you next week, possibly.
Oh, yeah, we got to plan on that, dude. We're missing some planning strategies here because shit's going on. So we gotta. I don't know your schedule, and I have holes in mine. I have a fair number of holes, but not many
Do you want to
ones.
come? Do you want to come visit Java One? I'll get you a pass.
Well, I don't have a ticket. I'm not going to pay money for one.
No, no, no. I'm sorry. I said, do you want to come? I'll see if I can get you a free pass.
Uh, um, I could roam around the halls and be melancholy about, or not melancholy, but reminiscing about the Java ones of yore.
Let me see what I can do.
All right, yes, but mostly I want to have a chance to, sit down with you face to face and have a beer and whatever.
That
And
sounds
is
like
there
fun.
going to be another wife along at some point? Mine would be
Nope.
probably interested if there was somebody she could talk to, and not if it's a room full of geeks.
No, I'm flying solo.
All right, fine. All right, let me kill the camera here. We're recording funny stuff. All right, bye bye.
Bye.
Bye.